In this video, we're going to talk about the property of alkenes. We will go on to what is an alkene, we'll then go on to drawing an alkene, and then talk about the restricted rotation, which leads to different reactions. Now, alkenes you'll be familiar in GCSE end in E-N-E. You have to name ones up to 10. So that means, when I say that, what I mean is number of carbons. This is our N here. So in A levels, anything from 2 through to 10. Now after that, you may have to draw the structures of alkenes that have over 10 carbons, but you won't have to name it. The naming only goes till 10. Now if we then go to the molecular formula, you can see 2 carbons, 4 hydrogens, 3 carbons, 6 hydrogens. So they have a general formula of CnH2n. Now all of these namings as well generally follow the shapes that you'll get in maths. So hopefully it shouldn't be too difficult. Now, alkanes are generally known as saturated. So alkenes are known as unsaturated. And we also have a carbon-carbon. It's really important you say carbon-carbon. Really important. That's what people miss off all the time. In A levels, there are carbon-carbon double bonds, and that's the other difference, bonds. You can have more than one double bond. In GCSE, it was just one double bond. In A levels, it is more than one double bond, potentially. General formula is CnH2n, ends in E-N-E, and there's that restricted rotation around the carbon and the carbons within the double bond. So now that we know our description of alkenes and what alkenes involve, let's do some naming and drawing. And there's nothing to stop you doing the drawings yourself, even if you want to just carry on and draw these right now and just put every single double bond at position number 1. But we're going to do it in stages. So first of all, we're going to do prop 1-ene. And prop 1-ene, prop meaning 3, okay, and there's your 3 carbons. We're going to put our double bond at position number 1, and then we're going to fill in all of the hydrogens around. Remember, there are 4 bonds to a carbon. So there you go. There's your hydrogen, another hydrogen there, and then there's all our hydrogens, and we just fill in the gaps. Okay. Now, if that's the case, if you're doing really well, you're probably thinking about bond angles at this point as well. And what we have is we have 3 bonding regions around there. So we've got a 120-degree angle between there as well. And there's also a 120-degree angle here. But again, think about it. What bond angle is this? This is 4 bonding pairs, so that is 109.5. Okay, so just a simple revision of bond angles as well. But this is prop 1-ene. Let's just write that here. So prop 1-ene. Now notice your numbering of where your alkene is, the number goes before your E. The next one we're going to do is do multiple double bonds. But because it's multiple double bonds, we are going to do it in skeletal formula, and we're building here. So try and do things in skeletal formula. It makes things easier and quicker. So the one we're going to do is pent, and it's pent 1,3-di-ene. Your di is telling you that there are 2 double bonds because the di is before the ene, and the 1 and the 3 tells you where they are. So and the pent will tell you how long it is. So pent means 5. So 1, 2, 3, 4, 5. Then you've got 1 and 3, so let's count where 1 and 3 is. 1, 2, 3, 4, 5. Then you've got 1 and 3 where the enes are. So there's 1 double bond, okay, and then there's 3, which is your 2 double bonds, okay. So we've now got pent 1,3-di-ene. So there's 2 double bonds right there. Now, I then go to our final example, which is going to be hex, okay, and that is hex 1-ene, 1-ol. Okay, so hex 1-ene, 1-ol. Now hex 1-ene, 1-ol, okay, means that what I've done is I've got this hex at the start, which is 6 carbons, so I'm going to draw 6. So that's 1, 2, 3, 4, 5, 6. Let's just join that up. Okay, so I've got 6 here. And a few things to notice. One, first of all, is the 1 here is before the ene. That's telling me my double bond is at position number 1. So my position number 1 is here. Let's draw that in again. Okay, so my double bond is there. Okay, then we've got 1 ol. Okay, so that is, first of all, it cut off the E that's at the end to put in an alcohol at the end. So if you're putting another group on the end, you have to take off the E and put whatever the suffix is. In alcohols is this case, but you'll be used to that as you do it across the course. So that means at position number 1, this is position number 1, 2, 3, just put a few numbers on there just to make it clear. And there you have your OH. Now, the mistake that a lot of my students do is they will not connect this bond, this carbon, to the oxygen. Sometimes they'll connect the carbon to the hydrogen and then have the O afterwards. And that's a clear error that happens all of the time. Okay, so make it really clear your bond is going to the atom that the carbon is bonding with. In this case, it will bond with the oxygen. Now that we can draw and we know the general properties of the alkenes, we're now going to look at this restricted rotation, which is really, really important. So here's your simple picture of ethene, and we're going to talk about how that causes this restricted rotation. Now, the answer for the exam is that the double bond is formed by these p orbitals overlapping, and it forms this pi bond. Okay, that's what you need to say. But I'm just going to go on and try and make you understand it a little bit. Now, what's really important is this pi bond is the one that breaks, and then that's how you form your other products from alkenes. But again, we'll go over that later. Now, why does this work? So here you have a general picture of the orbitals that are around each carbon. And we've got one of these p orbitals here. And you can remember the shape of a p orbital. The shape of the p orbital is a dumbbell. And you can see the overlapping of these orbitals. And here is your sigma bond, which is your single bond. And here what's forming is your double bond. Now the double bond, even though you see it as one, so if we put that there, you see it a double bond here, you see it as one line. Your double bond is both of these, we call them lobes underneath. And they're done from the p orbitals sideways overlapping to form a pi bond. Now, if we then do that and make that a bit obvious, there, you can see the purple is this bond here, and that bond is a sigma bond. What makes it into a double is this one here, which is your pi bond. So your pi bond is this, as you saw, the sideways overlapping of these p orbitals to form a pi bond. And it's this bond here that breaks to form these other products. The sigma bond stays intact. Okay, so if we just summarize that, here's your p orbitals. And in the video, we showed them sideways overlapping to form this pi bond above and below. Now, just want to talk briefly about the actual, what are these orbitals again? Remember, an orbital is a probability of an electron being in a space. So basically, the electrons in this p orbital are somewhere in this lobe here and somewhere in this lobe here. Now, as we move into a pi bond, those electrons that are in those p orbitals are more likely to be found here or here. It's just changing the likelihood of where you're going to find those electrons. And that means when they're over here, they're shared between these two carbons. When here, they're on their carbons. Here, they're shared. And that's your double covalent bond. All right? But let's just look at this in terms of what you're going to put in the exam. Okay? All you're going to put in the exam is that double bond is formed by the p orbitals overlapping. And it's actually important to put sideways overlapping in there. Okay, and it's sometimes really good to say that pi bond is above and below the plane of the single bond. You can see it here, above and below the plane. And it contains 2 electrons. When you're counting up electrons, really important, your pi bond is going to be 2 electrons, and your sigma bond is going to be 2 electrons. Now, when the reaction happens, as I've said, the pi bond breaks, but the sigma bond remains intact. We're now going to look at the bond angles, which are around that restricted rotation, okay, and show you what that is within an alkene and another different type of molecule. So trigonal planar, 120. So that's the thing you have to remember. But why is this? This is because 3 electron bonding regions, which repel each other as far as possible, and those regions make the bond angle around the carbons planar, which means flat. So if I look at planar, flat, I just like to do it like this. So here's a typical example of a trigonal planar with the 3 bonding regions around the outside. And you can see, if we just do the animation here, you can see they're totally flat. Now, if we just want to draw a couple of examples, so a simple example is going to be ethene. Okay, and there's your alkene. And I just want to go through quickly that electron bonding region. So the electron bonding region is made of a pair of electrons in the sigma bond, and then a pair of electrons in the pi bond. So you've got two pairs of electrons there. We've got another pair of electrons in the sigma bond between the C and the H, and another pair of electrons between the other C and the H, which means we have 1, 2, 3 bonding regions. The reason we call it bonding regions is because there are 2 bonding pairs inside there. So if you've got multiple pairs, you've got to call it a region, not a pair. Okay, so 3 bonding regions, and there's our 3 bonding regions around here. Now, I think it's also interesting just to introduce a different type of one that is also this trigonal planar, this 120 degrees around this central carbon. And you'll come across this slightly later, but these are called aldehydes. Okay, so I'm going to put an R group here. Now R, just remember, means any alkyl group going off, 1, 2, 3, 4 different carbons and things like that usually. It can be any group, but most of the time it's alkyl groups. Now if you look at this now, and we can do the same thing, this is an aldehyde. Okay, we have got a sigma bond there, pair of electrons. We've got this double bond here, which will be that pi again. Okay, and then we've got, there you go, and there you go. So we've got 3 bonding regions again. So this is also 120. So aldehydes have 120 degrees, and also alkenes 120 degrees. And they are both in themselves trigonal planar. And because of those 3 bonding regions, they're both planar, they're both flat.